In the previous class we talked about shear stress in beam bending, or the related idea shear flow in beam bending. We derived a formula for calculating shear stress at different points in the cross section of a given loaded beam, and we compared that formula with formula for bending stress, and we compared the profile of bending stress with that of shear stress. And today we'll talk about the last two problems I gave you for assignment, and I'll not exactly solve the problem, but I'll just describe the problem so that it's easy for you to solve it. So this was the question 3. A T-beam has the cross section shown in the figure. Calculate the shear stresses for the indicated 6 horizontal sections when the beam transmits a vertical shear of 240 kN. Plot the results. I forgot that part. Let's just calculate the shear stresses at various horizontal sections shown. So there are 6 horizontal sections mentioned here, 1 2 3 4 5 6, and location of each of them are clearly marked. So you just need to calculate the shear stress at these points. So this is not difficult, this is quite straightforward. Since we have the formula, we just need to apply it properly and get the answer. So the formula for shear stress is nothing but VQ by IT, and it's clearly given that beam transmits a vertical shear of 240 kilonewton. So vertical shear is given by 240 kilonewton. So that's straightforward. You don't need to calculate V from a given beam loading. It's directly given, no issue. Now what is I here? I here is the area moment of inertia about the neutral axis, or about the centroid, which you can very easily calculate. So here what will be I? Area moment of inertia about the centroid. So how do you calculate the centroid here? So split the area into two parts, A1 and A2. Okay, I'll just draw it together, right? A1 and A2, and of course A1 will have its centroid at the geometrical center of A1, and A2 will have its centroid at the geometrical center of A2, and the centroid of the whole area can be calculated by using the formula. It's I think you're very familiar with this formula for calculating centroid. So here in this case, that will be A1x1 plus A2x2 divided by A1 plus A2, and that will give you the centroid of the whole section. And let's assume that this is the value you obtained. So this value, centroid of the whole section. So centroid of the whole section. So once you have the centroid, you need to calculate the area moment of inertia of the whole section about the centroid. How do you do that? Again, you need to find out the area moment of inertia of individual rectangles, and then find out the area moment of inertia about find out the area moment of inertia of individual areas about its centroid, and then find out the area moment of inertia of A1 and A2 about neutral axis, and simply add them up. So you know the formula BDQ by 12, which you can use to calculate the individual area moment of inertia. And once you have that so the area moment of inertia of individual area plus area multiplied by a distance square. So this will give you the area moment of inertia about the centroid, of the whole section, right? So for example, if you are considering A1, first calculate the area moment of inertia about its own centroid. Once you do that, that quantity plus that area multiplied by d square, where d is the distance between centroid of the individual area and centroid of the whole section. So this will give you the area moment of inertia about the neutral axis or centroid of the whole section. So do the same for second area, A2d2 square, and add both of this up, and you'll get total area moment of inertia. Now t has value for 1, 2 and 3. For 1, 2 and 3, t is equal to, for 1, 2 and 3, t is nothing but the breadth. So for 1, 2 and 3, t is equal to 150, and that is millimeter. You need to take care of the units. And for 4, 5 and 6, T is equal to 50 mm, which is smaller. So when T is smaller, toe will be larger. Shear stress will be bigger when breadth is smaller. And the last quantity here is Q. Q is equal to A y bar. So in this case, A and y bar will depend on the section you are considering. And if you choose first location 1, this is the first location, so the area of the T section above this line is essentially 0. So 0 multiplied by y bar will give 0. So it's 0 shear stress at the topmost point, topmost layer, which is something we already know. Similarly for 6, there is no area below 6, so that also will be 0. But for 2, if you consider 2, for section 2, there will be an area here, and that area multiplied by distance between centroid of the whole section and centroid of the considered area. So the centroid of the area which we have shaded here will be the geometrical the centroid will be located at the geometrical center of the shaded area, and the distance between geometrical center of the shaded area and centroid of the whole section. So distance between these two will give you y bar. So this area multiplied by this y bar will give you Q for section 2. And similarly for section 3, section 3 is right here. So this will be the area we need to consider. This might be the area we need to consider, because we also need to actually locate neutral axis. Here I've simply assumed that neutral axis is between 4 and 5. If neutral axis is somewhere else, again you need to do the corresponding changes. So I'm simply assuming that neutral axis is here. In that case, this is the area we need to consider. So if neutral axis was here, we should have considered the area below it. So this is A, and y bar will be the distance between centroid of the whole section and centroid of the shaded area, y bar. So A multiplied by y bar will give you Q, which can be substituted here. Similarly for 5 and 6. For 5 is somewhere here, so this will be the area you need to consider. And A is the area of the shaded section, and y bar will be the distance between neutral axis of the whole section, the centroid of the whole section, and the centroid of the shaded area, which will be at the geometrical center. And that distance will give you y bar, and A multiplied by y bar will give you Q. And T, we already talked about T. So VQ by IT, this seems to be a very simple problem. You can actually do it very easily. Now let's look at the next problem. So please note that you don't need material property here. To calculate shear stress for a given beam with a given load and a certain shape and dimensions, you don't need material property. Now let's take the next problem. This problem seems to be a little more interesting and maybe not as straightforward as the previous problem. Still, let's have a look at it. So you have a steel cantilever beam which is fabricated from two structural T's welded together as shown in the figure. So this is essentially this looks like an I section which was obtained by combining two T sections. Determine the allowable force P that the beam can carry if the allowable stress in bending is 150 megapascal, in shear 100 MPa, and along the weld 2 meganewton per meter. So you need to note the units here. So the bending stress, maximum allowable bending stress is 150 MPa and maximum allowable shear stress is 100 MPa, and along the weld the maximum shear allowed is 2 meganewton per meter. So this 2 meganewton per meter is not exactly shear stress, it's the value of shear flow which we have talked about during the derivation. So you can also see that when it comes to welding two T sections together, bending stress will not be the major problem there. It's highly likely that shear will cause problems. Yeah, so let's look at the problem here now. So this is a T section. I section obtained by welding together two T sections. So the maximum allowable bending stress is 150 MPa, maximum allowable shear stress is 100 MPa, and maximum allowable shear flow is 2 meganewton per meter. So we have three constraints here. So what we will do is that we will calculate maximum allowable force P considering one constraint at a time, and you'll get three values of force, and we will choose the least value, smallest value among them, so that we can satisfy all three constraints. So starting with the sigma max, so the magnitude of bending stress, so this is downwards, it will cause negative moment, and you will have tensile stress at the top and tensile stress at the top and compressive stress in the bottom. And the maximum values of bending stress will occur at the topmost point and bottommost point. So sigma, let's call this point, this is the top point, this is bottom point. Sigma at the top will be equal to my by I, where y is the maximum possible bending moment. The maximum possible bending moment is P multiplied by 1000 millimeter, which is nothing but 1 meter. So P multiplied by 1000 millimeter, you convert the units properly, that will be the maximum bending moment. And my by I, what is y there? Y is the distance between neutral axis and the point which you are considering. So your next job will be to find out the location of neutral axis, which is nothing but the centroid of the whole section. So this is 200, 150, so let's call this A1, A2 and A3, and A1, centroid of A1 is located at this geometrical center, and keeping this point as a reference, bottommost point as a reference, x1 will be the distance between centroid of A1 and the reference A2. Geometrical center or centroid of A2 will be at the exact center, and x2, let's say x2 is the distance between the centroid of A2 and the reference. And similarly you have x3 here, where x3 is the distance between centroid of A3 and reference point. So the location of neutral axis, x centroid or xna, whatever you like to call it, that will be sigma xi ai divided by sigma ai for A1 x1 plus A2 x2 plus A3 x3 divided by A1 plus A2 plus A3. That will give you the location of centroid, and that is probably, that will be somewhere here, I believe. It won't be at the, it will be above the weld, because you know that this is 150, this is smaller, so the anyway, this is not the exact location, it will be somewhere here. Now once you locate xc, y will be the distance between this neutral axis and the topmost point, and then you have I. Again, there is a method to calculate I, so use the formula BDQ by 12 to calculate moment of inertia of all of these individual areas. Once you do that, using the distance between centroid of individual area and centroid of the whole section, you can calculate the area moment of inertia of individual area about neutral axis, and then add all of them up. You will get the I for the whole section. That will probably look, once you calculate IA1 using this formula, A1 multiplied by D1 square, where D1 is the distance between neutral axis and centroid of A1. Similarly, IA2 plus A2 D2 square, and IA3 plus A3 D3 square. So from these formulas you will calculate the area moment of inertia of individual areas about neutral axis, and add all three, and you will get the total I. So maximum moment of inertia, maximum bending moment, area moment of inertia, and Y, you can calculate sigma t. Similarly, you can calculate sigma bottom. So there the only difference will be, there will be a different value of Y. So so here T, which will be the maximum value of bending stress here, top or bottom? That depends the value of M by I into Y, and M is same for both, I is same for both, and the only quantity that varies is Y, and the bigger value of Y, sigma B will have the bigger value of Y, and hence this is the quantity we are interested in, not sigma T. So this is something you will figure out once you calculate the centroid neutral axis. You will find that it's little bit on the upper side, and value, the Y for sigma bottom will be larger than top. So sigma bottom will be the value we are interested in. So from that you will get a P. So that sigma max can be equated with the given sigma max. So sigma bottom can be given 150 MPa, which is equal to I is calculated, Y is calculated, M is some quantity into P, so a constant multiplied by P will be the answer, and you will get the value of P from here. So we will call this P1. Okay, you have a value of P1 here, and then using the idea that maximum shear stress allowed is 100 MPa, if maximum shear stress allowed is 100 MPa, tau is equal to, what is the formula for tau? That is VQ by IT. VQ by IT, and shear force is P here. Shear force is 0 on the right side of P, and shear force is P on the left side of P, left side of point of action of P. So V is equal to P, and I is again the same, we have already calculated it. T value depends on the point which we are considering, and you also have Q. Now for unlike bending stress, the maximum value of bending stress happens at the farthest point from neutral axis, but the maximum value of shear stress happens at the neutral axis itself, the closest point to neutral axis or the neutral axis itself. So you can find out the value of tau at the neutral axis. How do you calculate that? Once you have this TA, you can find out the area of the section above neutral axis, that will be A, and then find the centroid of the shade area using the formula. Using this type of formula, you can calculate the centroid of the area, which will be somewhere here probably, and the distance between that and the neutral axis will give you y bar. So once you have A and y bar, you will get Q. So you have Q there, and V is equal to P and I you've already calculated, and T, you are finding out shear stress at the neutral axis. So at that point, T is equal to thickness, which is 25 millimeter. This is 25, right? I'm not sure. Yeah, I think it's 25. Yes, 25. So give that value of T and you'll get tau. So this quantity is equal to P, and we will call that P2. So you have a different value for P2. So you have calculated the maximum allowable force using two techniques, and you have one more constraint. The third constraint is that the shear flow at the weld point is 2 meganewton per meter. So Q max sorry, why did I write P equal? It's not equal. This is not equal to P. V is equal to P. So here you will get a value of P, and that will be called P2. Okay. So V is equal to P. Tau is given here, 100 MPa. Other quantities are calculated, and you will get the value of P2. So P3, like I told, you will get it due to the constraint that the maximum value of shear stress at the weld point is 2 meganewton per meter. So shear flow, sorry. So the equation for shear flow is that Q is equal to VQ by I. So here V is equal to P, and I have already calculated. And what is Q? Q is again A y bar. What is A? A is the area below the weld point. This is A. Q is equal to A y bar. This is the A here. And y bar. How do you calculate y bar? Find the centroid of this shaded area using this type of formula. So it will be somewhere here, and the distance between neutral axis and centroid of this shaded area will give you y bar. So A multiplied by y bar will give you Q. So once you have Q, it can be substituted here. So the Q max is given here, which is 2 meganewton per meter, which is the maximum allowable shear flow. So from there you will get value of P, which is P3. So you will get P1, P2 and P3 due to three different constraints. So to satisfy all three constraints, you have to choose the smallest among P1, P2 and P3, and that will be the answer you're looking for. So that's with that we have talked about all problems given in the assignment. So I think you can now go ahead and complete the assignment and submit it as soon as possible. So I will close the lecture today.